last topic in chapter 9 that we need to consider is the reaction of the sulfur analogs of alcohols and ethers. The sulfur analog of an alcohol is called a thiol, and the sulfur analog of an ether is called a sulfide. So a thiol has an SH group on it. Okay, thiol, for example, and a sulfide has two R groups. Dimethyl sulfide as an example here. The chemistry of these is dominated by the fact that the sulfur is larger and more polarizable than the oxygen. And that means that this is simply more acidic than an alcohol. And it means that even the neutral sulfur is a good nucleophile because of the polarizability. Because of the increased acidity of the SH group as opposed to the OH group, it doesn't take a base any stronger than hydroxide to remove that. So you can readily generate the corresponding sulfur anions just by treating with hydroxide. And that reaction is effectively irreversible, because the thiol tends to be at least 3 orders of magnitude more acidic than the corresponding alcohol, or in this case, water. Oops. Took that hydrogen off. So we can readily generate the sulfhydryl anions, and these sulfhydryl anions are excellent nucleophiles, but pretty weak bases because of the increased acidity of the sulfhydryl group, or thiol group. So we can use them productively in SN2 reactions. And we saw an example of using a CH3S minus group to displace the oxygen in epoxide on the previous video. But these will react with any alkyl halide. So if we were then to react this with the corresponding primary alkyl bromide, we would expect to get a nice SN2 reaction, even with the beta branching in place. To generate sulfide. So the most common way that sulfides are made is by starting with thiols, deprotonating with a base, and then using that negatively charged sulfur to do an SN2 reaction. And here I've made an unsymmetrical sulfide. Even the sulfide, though, can do an SN2 reaction if confronted with an unhindered molecule with a good leaving group, like iodimethane, for example, to generate sulfonium salts. And these salts are excellent SN2 substrates themselves that can react with other nucleophiles. Because the neutral biological systems, the sulfur of methionine, which has an SCH3 group at the end of it, amino acid methionine, is often used as a methyl transfer reagent. Methionine can be methylated, and then the corresponding sulfonium salt can leave as a neutral leaving group. This doesn't happen readily with ethers. The larger, more polarizable sulfur is a much better nucleophile than the smaller, less polarizable oxygen. So we can alkylate S minuses using alkyl halides, but we can also alkylate neutral sulfides to form sulfonium salts. And that's a reaction that isn't typical of the oxygen analog. The other characteristic of sulfur that makes it different from the oxygen is its ability to expand its octet. Because sulfur is in the third row, there is a D shell, and that allows the sulfur to be oxidized using a variety of reagents, whereas the oxygen would not. So thiols like 4-methylthiophene here. When treated with strong oxidizing agents, like KNO4, or 30% hydrogen peroxide, will oxidize to the corresponding sulfonic acids. So here we have para-toluene sulfonic acid. Para-toluene sulfonic acid can be converted to the acid chloride using the very strong chlorinating agent PCl5. This is an acid chloride of phosphoric acid. To create the sulfonyl chlorides that we needed in order to convert alcohols into cosylates or mesylates or triflates, and thus convert them into good leaving groups. This is a nucleophilic acyl substitution reaction, but it's a reaction that we won't bother you with the mechanism of until the second semester course, when we talk more about acids in general, carboxylic acids and carboxylic acid analogs. So the sulfur can be oxidized with expansion of the octet by addition of 3 oxygens. And remember that one of the definitions in organic chemistry for oxidation is addition of oxygen. Loss of a pair of hydrogens or addition of an oxygen. Potassium permanganate and 30% hydrogen peroxide are both very strong oxidizing agents. If you take a thiol and you treat it with a less strong oxidizing agent, so drugstore variety, 3% H2O2, or iodine in water. Iodine is an oxidizing agent, but not as strong as potassium permanganate. You can take a thiol and you can create from that thiol a disulfide. This reaction takes away 2 hydrogens. And the example I'm going to use here is the amino acid cysteine. Cysteine, which is the amino acid, alpha amino acid to the there, can be converted into the disulfide. Which is the same molecule without the E. And this is the disulfide form. This thiol to disulfide reaction is important in protein folding. The disulfide bridges create the protein secondary structure that is sometimes essential in identifying or in producing the desired function for an enzyme. So mild oxidizing agents, iodine, water, or 3% hydrogen peroxide, oxidize by removing two hydrogens to create a disulfide bridge. Which is the sulfur analog of the peroxide. Ethers form peroxides upon exposure to air. This would be diethyl peroxide. And that's the analogous compound to the disulfide ring. Peroxides, however, tend to be explosive. Diethyl ether will spontaneously form diethyl peroxide upon exposure to air, and then if it's evaporated, the diethyl peroxide explodes. So one has to be careful how to storing the ether in an inert atmosphere and using it promptly before it forms peroxides. So the sulfide is the sulfur analog of an ether, and the disulfide is the sulfur analog of a peroxide. Stronger oxidizing agents will oxidize the sulfur with the addition of 3 oxygens to form sulfonic acids. Sulfides react with the stronger oxidizing agent, 30% H2O2, to expand their octet. And the product of oxidizing sulfides with strong oxidizing agents we have diisopropyl sulfide. Diisopropyl sulfide can be oxidized with 30% H2O2 to the corresponding sulfoxide. The addition of 1 oxygen and with the addition of a second oxygen to diisopropyl sulfur. There are no oxygen analogs of sulfoxides or sulfones. Because oxygen can't expand the octet and add additional oxidants. So a sulfoxide is a sulfur oxygen double bond, and a sulfone has a pair of sulfur oxygen double bonds where we oxidize by adding 1 oxygen and then adding a second oxygen. It's not easy to stop at the sulfoxide stage, but it can be done if you use the limited amount of the hydrogen peroxide. The mechanisms for these reactions are magic. You just write down poof. So all you need to know is that these reactions occur. Most of these oxidation reactions are not reversible, but there is an exception. The disulfide can be converted back into the thiol using a suitable reducing agent. reaction is referred to as the dissolving metal reduction. And the reagent is an alkali metal, often lithium, and ammonia liquid, which has a boiling point of minus 33 degrees C. Lithium is so reactive and such a good reducing agent, wants to give up its electron so badly that it would actually give it up to ammonia. And you will end up with lithium cation surrounded by the partially negative nitrogens of ammonia. Nice solvent shell and an electron just sitting by itself in solution, surrounded by the partially positive hydrogens of the ammonia. As you might imagine, an electron floating around by itself in solution, which we refer to as the solvated electron, is a very powerful reducing agent. It's a deep blue solution. Just take lithium metal, dissolve it in ammonia at minus 33 degrees C, and it turns from colorless to a dark blue solution. The electron interacting with the partially positive hydrogens of the ammonia solvent. This will react with disulfides. Liquid ammonia solvent, followed by acid workup to liberate two molecules of thiol, effectively doing the reverse reaction in the reaction that formed that disulfide, which was iodine. Water doesn't have to be water, it can be other solvents, but iodine water is a common oxidizing agent, or 3% iron peroxide. So we can convert freely back and forth from thiol to disulfide and disulfide back to thiol. If you model the molecular orbitals of the disulfide, you'll find that the LUMO orbital of the disulfide is actually a sigma star orbital. And that LUMO is associated with the sulfur-sulfur bond. So if I use my pink and yellow chalk to color code the positive and negative sign on the wave function, you'll see that there's a node right down the center between the sulfurs. If we donate an electron into that orbital, we thus weaken the sulfur-sulfur bond. So you could propose that an intermediate in this reaction in that sigma star orbital, thus weakening this bond. A radical anion caused by the donation of the single sulfated electron surrounded by ammonia into the sigma anti-bonding LUMO. Once you form that and you weaken that bond, homolytic cleavage of the sulfur-sulfur bond would result in a negatively charged sulfur on one side and the sulfur radical on the other side, and it would take very little for that sulfur radical to pick up an additional electron from the solution to generate the second molecule CH3S minus, and there it will sit as the lithium salt until you work this up with aqueous acid, because ammonia has a pKa of 35, which is nowhere near a good enough acid to protonate the sulfur group. But if you work this up with aqueous acid, the CH3S minus will pull off a hydrogen to form the thiol. 2 equivalents of acid will be required. Generally, you just use large excess of aqueous acid. So the dissolving metal reduction will convert the disulfide into the thiol.